E squared, and you write a density of states, this is density of states, times the diffusion coefficient. This is a general Kubo formula, which I have not derived here. Just take it for granted. And so it's clear that D is related to tau. So what's the relation between D and tau? Just as I have this, if I work in the velocity space, it turns out that D is in fact is like the Fermi velocity times tau. Remember, Dr. Dattagupta pointed out that the velocity that we are talking about characteristically is just a Fermi velocity. And so what is tau? Tau itself is that, let's go once think about Maxwellian kinetic theory, that tau is the mean free time between two collisions. So the mean free time between two collisions is the mean free path divided by the Fermi velocity. So this term I want it as, sorry, it's VF, right. So VF, yeah, so VF I got dimensionally correct, yes. So it's actually VF times VF tau, and that's exactly what Mr. Mitchell said, is that it's VF times L, the mean free path. Okay. So you see that, so conductivity is proportional to tau, and tau is the mean time between two collision events, right? So clearly tau is temperature dependent, right? Because if I increase temperature, then the electrons become more vigorous, right? They bump into each other more often. So what will happen if the temperature increases? Tau would decrease, correct? Right? Tau would decrease. So if tau decreases, then the resistivity rho is actually inversely proportional to the conductivity. So resistivity is therefore proportional to 1 over tau. So if tau decreases, my resistivity increases, which is intuitively, we all know that if my temperature increases, then the resistivity increases, right? Okay. So this part is fully understood, that rho of t, if you plot versus t, then resistivity increases, and you have d rho dt, the slope of this is actually positive, right? It's like dy dx, the slope is positive. This is the diagram that you always draw, because if you have a superconductor, then at some temperature resistivity will drop down to 0 here, and you have 0 loss transportation. But then it was Mui who looked at various samples in 2 dimensions, Dutch physicist, and he found out, and these are disordered systems, and he found out that at some sufficiently low temperature, d rho dt, the resistance again starts increasing, but the d rho dt slope is actually negative. Okay, and this is due to the localization transition. So this phenomenon, it's an experimentally observed phenomenon that that you find out that the slope of the resistivity changes in sign. So that's Mui's work, and I have some data here. So these are techniques where you can calculate this scattering time. it's called Bloch-Boltzmann-Weak scattering theory, they break down. You need new theories. Actually, you need scaling ideas. Sometimes the physicists try to use perturbation theories, etc. But when you have strong correlations, strong disorder, perturbation theories fail, and just as you saw, or you probably heard of, that in the theory of phase transitions near critical point, no perturbation theory works, so therefore you have to do renormalization group theory to calculate things, critical exponents, etc. So scaling ideas come in. So in 2D, one of our own senior colleagues was involved. There's this T.V. Ramakrishnan with Anderson, Ricciardello on what happens to localization in 2 dimensions and the scaling theory. So newer theories come in to explain such phenomena. Yeah, you have to make that.
Yesterday you were telling that one as relaxation time. So I want to know that the relaxation time and scattering time both are same or?
In our picture, the nomenclature is the same. Okay. The relaxation time, of course, also comes in your NMR, for instance, like when you have T1, T2 processes, like in the Bloch equations. But here, is relaxation.
If I consider this as scattering time, then I think sigma increases as time.
So we call it the scattering time because the whole picture is that the electrons get scattered as they move from one part of the sample to the other.
But if you consider relaxation time, then.
So only name, na? So what is relaxation? When something relaxes back to some equilibrium, and more often exponentially in simple cases, we call that rate of going to whatever constant value is like a relaxation rate, or the inverse is relaxation time. So here also, when you have the tau would scale like 1 over gamma, and so if you had nothing, v of t at time, v as a function of time, will fall off as exponential minus gamma t, correct? Right? Because v dot is minus gamma v. So you solve that equation, the simple first order differential equation, dv dt is minus gamma v, so v of t is e to the minus gamma t. So things fall off exponentially as e to the power minus t over tau. And that's why you call it a relaxation time. The v of t relaxes to equilibrium with a characteristic time scale tau. But the way the model is set up, it's like a scattering time because you think that the electron, while moving from one part of the sample to the other, encounters many collisions. Vaguely you put that because these collisions could be with defects, disorder, or could be phonons, etc., etc. And so the velocity will keep on changing its direction as well as in its magnitude. Magnitude will change if you have inelastic scattering. So then, in analogy with the classical kinetic theory of Maxwellian gas, you say tau is the mean time between two successive collisions, and therefore it's either a collision time or a scattering time. Okay. So in this context, think of it as a scattering time. All right. So what I was saying is that, so let me just read out again. So in particular, the temperature dependence of the resistivity becomes much weaker and eventually changes direction for high enough disorder. There's some empirical rule called the Mathiasen rule, according to which the contributions to rho due to disorder and temperature are additive, thus breaks down. All those rules break down. So μ spelled as M-O-O-I-J, so we found that d rho dt becomes negative when rho becomes larger than the value ranging around, so rho is becoming in magnitude larger and rho becomes larger in the range around 80 to 180 micro ohm centimeter. So rho is the resistivity. So remember from Ohm's law considerations, your resistance is rho L over A, so therefore resistance has the dimension of, rho has the dimension of resistance, which is in micro ohm that you have written down, times the dimension of a length because it's A over L, and that's why the centimeter comes in. So, in hundreds of disordered systems that he looked at samples, and so this was considered to be universal. A whole lot of samples showed this. There's something very universal happening, especially in two-dimension. Things happen in a very interesting way, which I'll show you. And this properties weakly depend on material properties. It's almost universal. It's like your law of corresponding states. When you have a van der Waals equation, you found that many gaseous elements could be actually put on the same graph if you scaled your pressure by the critical pressure Pc, T by Tc, and volume by Vc. Then you have a universal law of corresponding states. So it's like a law of corresponding states, and so therefore you see now. So when would the Drude theory fail? See, Drude theory. So in this region, the Drude theory is going to fail because you have a lot of disorder. So Drude theory, it assumes that I have a sample length L, let's say, well, capital L, because I use L as mean, small l as mean free path. Sample length L, and the electron, while traversing this sample, suffers many collisions. So its phase, quantum phase, gets completely decohered. It's called incoherent transport. So your sample length scale is much larger than your mean free path, right? So now, it also means that if I have an electron wavelength lambda, so there are three length scales. One is the sample length scale L. The other is the mean free path length. And the third length scale is actually the wavelength associated with the electron. So the wavelength associated with the electron, because the electron is a wave packet, lambda f is nothing but 2 pi over kf. Definition. So these are all Fermi, right? Because this is all coming from the Fermi energy. Remember, we had defined the Fermi energy as the energy at which your Fermi distribution function goes to 0, and this value is equal to 1, and this is what your product versus epsilon. So once you specify epsilon f, you have actually, you can get everything, like you get kf from the relationship that a bar squared kf squared by 2 times mass of the electron is ef. So once you have ef, you can calculate kf, and from kf you can calculate the lambda f, the wavelength. So this is the lambda f associated with the wave, with the electron, which is like a quantum particle. So the Drude scattering theory, it works when your lambda f is actually much smaller than the mean free path, L. And L itself is Vf times tau, as we saw. So therefore, it means that it works when Kf times L. So what you do is you multiply on the right hand side by Kf, you get a factor 2 pi here. So this is much larger compared to something of the order of 1, because 2 pi, there's a factor 2 pi there on the left hand side. So this criterion will break down. When it does break down, then you can no longer use the Drude theory. So you have to also have an understanding of the limitation of a theory. So in a strongly localized states, where the Mui criterion shows that the resistivity is actually changing its slope, your ideas break down. And so that leads us to the notion of what is called the minimum conductivity. So let me just write that in 2 dimension. Something very interesting happens. And our focus has been on 2 dimension. So in 2D, 2D, sigma, the Drude conductivity, has this structure, E square over H bar, well, E square, yeah, E square over H, times KFL. So, see, KFL is a sample dependent property, right? Because L is the mean free path. Kf, of course, it depends on temperature and other things. It depends on the electron property. Times a fundamental constant, E square over H bar. So, if KFL is of the order of 1, then of course this Drude theory will break down. And so, when KF L becomes of the order of 1, sigma is of the order of E square over H, and then you have a maximum, so this is the minimum conductivity, and corresponding to that is a maximum universal resistance, which is given by the inverse of this. This is H over E squared. And just you put the values, so it's like 30 kilo ohm, which means that the resistance cannot be pushed beyond this limit. Okay? And so this is also called the Ioffe-Regel criterion in the context of localization. So, I mean, I'm talking things in a very qualitative way, and the fact that in 2D you have this universal resistance concept at very low temperature, and so the entire physics of the localization problem, which theoretically is a very hairy issue because you have to do renormalization group, sigma module, etc., etc. These are all words that I am using, jargons. We are not going to discuss any of these things. So things are very exciting. The 2D world is exciting. What happens in 1D, the general ideas of this gang of 4 people, I mean, Abrahams, Anderson, Licciardillo, and Ramakrishnan, showed that all states in 1D will get localized if you have impurities in 3. And in 2D, there are some interesting scaling ideas. We have these concepts of maximum resistivity or maximum resistance and lowest minimum conductance. So, which means that if states get localized, then of course you have very small value of conductance, and so you get into the insulating regime. Okay. Now these are also in the context of phase transitions. These are very exotic phase transitions, because see, normally what happens in a phase transition, like for instance water, okay? All of you know how to draw the phase diagram of water. This is something that you learn in school, that so for water, H2O, if I plot pressure versus temperature, then I need some colored chalks. I have 3 distinct phases, right? So, which phase is this? Huh? Yes. So this is high temperature and low pressure. So that's the gas phase. This one? Very good.